Hello students, I welcome you to the lecture number 3 on thermodynamics. In lecture number 1 and 2, we studied about thermodynamic terms, applications, work, enthalpy, heat capacity, measurement of delta U and delta H, that is calorimetry, enthalpy change, delta RH of a reaction, enthalpy changes during phase transformations, and enthalpies for different types of reactions. The link for lecture number 1 and lecture number 2 are given in the description part of this video. In today's lecture, we will study about spontaneity, Gibbs energy change, and equilibrium. These are very important topics which from your examination point of view, please listen to my lecture attentively and note down all the important points. I welcome you once again. Spontaneity. Before we learn about the spontaneity, I would like to draw your attention towards the first law of thermodynamics, which tells us about the relationship between the heat absorbed and the work performed on or by a system. It puts no restrictions on the direction of heat flow. However, the flow of heat is unidirectional from higher temperature to a lower temperature. In fact, all naturally occurring processes, whether chemical or physical, will tend to proceed spontaneously in one direction only. For example, a gas expanding to fill the available volume, burning carbon in dioxygen giving carbon dioxide, etc. are examples. Hence, we will continue with the description of spontaneous and non-spontaneous processes. A spontaneous process is a process that occurs in a system by itself. That is, when once started, no action from outside the system is necessary to make the process continue. Spontaneity means having the potential to proceed without the assistance of external agency. One aspect of spontaneous reaction or process is that it cannot be reversed on their own. That is, the direction cannot be reversed on their own. Thus, a spontaneous process is an irreversible process and may only be reversed by some external agency. It is a process which needs no work. On the other hand, a non-spontaneous process will not take place until and unless some external action is continuously applied. Examples of non-spontaneous processes are, that is, lift a body from the ground level to a higher level, or to fill a overhead tank, water tank, or to move a stationary car, etc. Thus, we can conclude that if a process is spontaneous, the reverse process is non-spontaneous. All spontaneous and most of the non-spontaneous processes are possible. Spontaneous processes occur naturally, whereas non-spontaneous processes require the help of an outside agency to occur. Now we will consider diffusion. The gas molecules move from higher concentration region to lower concentration region as shown in the diagram on the screen. So this diffusion is shown here. Here the left side is a higher concentration of molecules, and the gas molecules, when it is allowed to mix with the gas molecules of a lower concentration, they move, and they move naturally without external aid. The spontaneous process here is a natural process. the tendency of the molecules of the two gases, that is one on the left side and another on right hand side, to achieve maximum state of mixing. So when once they are mixing, a disorder occur. Another example is heat transfer. Heat always transfers from hot region to cold region without external aid. Please see the figure on the right hand side. Here, heat is getting transferred from hot body to lower body. Entropy. The thermodynamic property related to the disorder, which we discussed in the previous slide, of the system is called entropy, and it is denoted by the symbol capital S. The entropy is the measure of disorder or randomness in a system. The greater the disorder in a system, the greater is the entropy. For a given substance, like solid crystalline state is the most ordered state, hence its entropy is lowest. In the case of gases, gases are the most disordered state, hence its entropy is maximum for the gases. Whereas in the case of liquid state, the disorder is intermediate between the solid and the gaseous state. Another point is entropy of any system or any substance increases on heating. In a chemical reaction, entropy increases if there is an increase in the number of moles of gases during the reaction and vice versa. If the number of moles increases, then entropy also increases. A system at higher temperature has greater randomness in it than one at lower temperature. Thus, temperature is a measure of average chaotic motion of particles in a system. Consider the examples shown on the screen to explain the entropy of system. Here, there is a hot body Q on the left hand side, A on the left hand side, and its heat is Q. And because it is, and this system, its entropy can be represented by a symbol capital S subscript A, SA, and its temperature is TA. It is brought in contact with a cold system on the right hand side whose heat is Q, and the heat gets transferred from hot body to cold body. Hence, the hot body, the heat is minus Q, negative. Entropy is negative, and the entropy of the cold body is positive because heat moves from left to right. And let the entropy of the system be SB and temperature be TB. So the entropy of hot body A is SA is equal to minus Q by TA, and entropy of the cold body is SB is equal to plus Q by TB. When a system changes from one state to another, the change of entropy is delta S is equal to Q by T. Let it be equation 1. The total entropy change is given by the total entropy change is equal to entropy change of system plus entropy change of surroundings, which is always greater than 0. Let it be equation 2. The entropy of a spontaneous process increases till it reaches maximum at equilibrium. The change in entropy is 0. Since entropy is a state property, we can calculate the change in entropy of a reversible process by applying the equation delta Cis is equal to del Q Cis reversible divided by T. We find that both reversible and irreversible expansion for an ideal gas under isothermal condition delta U equal to 0. Therefore, delta S total is equal to delta surrounding, but which is not equal to 0 for irreversible process. Let us solve some two examples for understanding the concepts of entropy. Question number 1. Predict in which of the following entropy increases or decreases. 1. Subsection 1. A liquid crystallizes into a solid. Number 2. Temperature of a crystalline solid is raised from 0 Kelvin to 115 Kelvin. And part 3 of the question is 2 NaHCO3 in solid state decomposes to form Na2CO3 in solid state plus CO2 in gaseous state plus H2O in gaseous state. This is the equation wherein the changes are taking place. And part 4 is H2 gas gets converted to 2H gas. Part 1. Answer. After freezing, the molecules attain an order state and therefore entropy decreases. Part 2. At 0 Kelvin, the constituent particles are static and entropy is minimum. If the temperature is raised to 115 Kelvin, these begin to move and oscillate about their equilibrium positions in the lattice and system becomes more disordered. Therefore, the entropy increases when temperature of a crystalline solid is raised from 0 Kelvin to 115 Kelvin. Part 3. The reactant in this chemical reaction is NaHCO3 is a solid and it has low entropy. As you know, all solids have low entropy as compared to gases and liquids. Among products, there are one solid on the right hand side and two gaseous states. Therefore, the products represent a condition of higher entropy. So, the entropy increases. Part 4. In part 4, H2 gas becomes 2H gas. Here, one molecule gives two atoms, that is, number of particles increases, leading to the more disordered state. 2 moles of hydrogen atoms have higher entropy than 1 mole of the dihydrogen molecule. Next question. Question number 2. For oxidation of iron, 4Fe in solid state plus 3O2 gaseous combine react to form a product 2FeO3s. Entropy change is minus 549.4 joules per Kelvin per mole at 298 Kelvin. In spite of negative entropy change of this reaction, why is the reaction spontaneous? So, given that delta RH, that is standard reaction enthalpy for this reaction is minus 1648 into 10 to the power of 3 joules per Kelvin per mole. So we have to give the reaction. Why is the reaction spontaneous? Answer. One decides the spontaneity of reaction by considering we know that delta S total is equal to delta S system plus delta S of surroundings. So delta S of surrounding equals minus delta R H naught at temperature T. Entropy change of surrounding is delta surrounding is equal to minus delta R H naught divided by T at constant pressure. Therefore, we can write it as substituting the values. Delta R H naught is minus 1648 into 10 to the power of 3 joules as given in the question. Joules per mole, that is equal to divided by 298 Kelvin. Simplifying, we get the answer as 5530 joules per Kelvin per mole. Thus, the total entropy change of this reaction is delta Rs total is equal to 5530 joules per Kelvin per mole plus 549.4 joules per Kelvin per mole, that is equal to 4980.6 joules per Kelvin per mole. This minus 549.4 is given in the question itself. This shows that the above reaction is spontaneous. We have seen that for a system, it is total entropy change delta S total which decides the spontaneity of the process. For most of the chemical reactions, there are changes in both enthalpy and entropy. Neither decrease in enthalpy nor increase in entropy alone can determine the direction of spontaneous changes for this system. Hence, a new thermodynamic function, the Gibbs energy or Gibbs function, is defined, which is given by the relation capital G is equal to capital H minus T into S, where G is the Gibbs function, capital G is the Gibbs function, and H is the enthalpy, and T is the temperature, and S is the entropy. The Gibbs function G is an extensive property and a state function. The change in Gibbs energy for the system can be written as the change. So applying delta sign to the equation number 3. Delta G sys is equal to delta H system minus T into delta S system minus S into delta T. Rearranging at constant temperature, delta T is equal to 0. Hence, the last term in the previous equation is 0. Therefore, delta G sys equals delta HS system minus T into delta S system. Therefore, delta G is equal to can be written simply removing the sys subscript. We can rewrite the above equation as delta G is equal to delta H minus T into delta S. Let it be equation 4. Thus, the Gibbs equation is Gibbs energy change is equal to enthalpy change, that is delta H, minus temperature capital T into entropy change delta S. Dimensionally, delta G has units of energy because both delta H and T delta S are energy terms. And T into delta S can be written as K Kelvin joules per Kelvin, that is equal to joules. Temperature T is in Kelvin, Delta S is joules per Kelvin. So that becomes joules. Increase in enthalpy of the surrounding is equal to decrease in the enthalpy of the system. Therefore, entropy change of surroundings is equal to delta S subscript surrounding, that is equal to delta H surrounding divided by T, that is equal to system surrounding, that is equal to, because enthalpy decrease, therefore minus delta H system divided by T. This is nothing but enthalpy is of the surrounding is equal to the decrease in the enthalpy of the system. Therefore, delta S total is equal to delta S syst plus delta S surrounding, or delta S total can be written as delta system plus minus of delta H system divided by T. Rearranging or multiplying both left hand side and both right hand side by T, we get T into delta S total equals T into delta S system minus H delta H system. So for spontaneous process, delta S total is always greater than 0. Therefore, the T into delta S system minus delta Hs, that is the right hand part of this equation, should be greater than 0. That implies that minus of delta H system minus T into delta S system should be greater than 0. Using equation number 4, that is delta G is equal to delta H minus T into delta S, we can write that minus of delta G should be greater than 0, or delta G is equal to H into delta sys minus T into delta S system should be less than 0 for a spontaneous process. Let it be equation 5. So remember, Gibbs free energy change is given by the relation delta G is equal to delta H minus T into delta S. This formula you will be required, you need it while answering the numerical problems. So always remember, very important, if delta G is less than 0, then it is a spontaneous reaction. If delta G is greater than 0, then it is a non-spontaneous reaction. If delta G is equal to 0, then it is the equilibrium state. So these important points is repeated once again on the chart shown on the screen. So delta G less than 0, it is spontaneous. Delta G greater than 0, non-spontaneous. And delta G equal to 0 is equilibrium. So similarly, we can write a chart. Delta H is delta H, delta S and delta G. So it is given delta H minus delta S positive, then spontaneous. If delta H is positive and delta S is minus, non-spontaneous, that is, we substitute in the equation positive and negative and conclude here from the value of delta G. So the reaction, and another is the relationship with temperature. The reaction is spontaneous if T is greater than delta H by delta S. So the reaction is spontaneous above a specific temperature. The reaction is non-spontaneous below a specific temperature, below a specific. That is, T, if T is less than delta H by delta S, then the reaction is non-spontaneous. Further, it is shown clearly in this table 1. That is, effect of temperature on spontaneity of reaction. So delta H, delta RH, delta RS or delta RG. These all the three are standard changes in enthalpy, entropy and Gibbs constant. So if delta RH is negative, delta RS is positive and then delta RG is negative. So it is spontaneous at all temperatures. If all the three constants, that is standard and changes, are negative, then spontaneous at low temperature. If delta R is minus and delta RS is minus and delta G, that is all the three standard, is plus, non-spontaneous at higher temperatures. If all the three are standards are positive, then non-spontaneous at low temperatures. If delta RH is positive, delta RS is positive and delta RG is negative, it is spontaneous at high temperatures. So if delta RH standard positive, delta RS standard negative and standard delta RG is positive, non-spontaneous at low temperature. Entropy and second law of thermodynamics. For an isolated system, the change in energy remains constant. Therefore, increase in entropy in such systems is the natural direction of a spontaneous change. This is nothing but second law of thermodynamics. The second law of thermodynamics explains why spontaneous exothermal reactions are so common. In exothermic reactions, heat released by reaction increases the disorder of surroundings and the overall entropy change is positive, which makes the reaction spontaneous. The next is absolute entropy and the third law of thermodynamics. The entropy of any pure crystalline substance approaches zero as the temperature approaches absolute zero. That means if the temperature approaches absolute zero, the entropy of any pure crystalline substance also becomes zero. This is the third law of thermodynamics. Please remember. There is perfect order in a crystal at absolute zero. The statement is confined to pure crystalline solids because theoretical arguments and practical evidences have shown that entropy of solutions and supercooled liquid is not zero at 0 Kelvin. The importance of third law of thermodynamics lies in the fact that it permits the calculation of the absolute values of entropy of pure substance from the thermal data alone. For pure substance, this can be done by summing Q reversible divided by capital T increments to 0 to 298 Kelvin. Standard entropies can be used to calculate standard entropy changes. Gibbs energy change and equilibrium. The knowledge of the sign and magnitude of free energy change of a chemical reaction helps us to predict the spontaneity of chemical reaction as well as to predict the useful work that could be extracted from it. So far, we had considered free energy changes in irreversible reactions. In this section, we will examine the free energy changes in reversible reactions. The reversible under strict thermodynamic sense is a special way of carrying out a process such that system is at all times in perfect equilibrium with its surroundings. When applied to a chemical reaction, the term reversible indicates that a given reaction can proceed in either direction simultaneously so that a dynamic equilibrium is set up. This means that the reaction in both the directions, forward and reverse, should proceed with a decrease in free energy, which seems impossible. It is possible only if at equilibrium the free energy of the system is minimum. If it is not, the system would spontaneously change to configuration of lower free energy. So, the criterion for equilibrium is A plus B, both forward and reverse form C plus D, is delta R G should be equal to 0. The standard delta Rg is related to equilibrium constant K of a reaction as follows. That is, 0 is equal to delta Rg naught plus Rt into natural log of K. Here the capital K is the equilibrium constant. Don't get confused with the letter Kelvin. Delta Rg naught is equal to minus Rt natural log of K. That is rearranging the above equation. So delta Rg naught equals minus 2.303 Rt log of K. That means in equation 6 we have converted the natural log into the log to base 10. So therefore delta Rg naught is equal to delta RH naught minus T times delta R S naught. That is the Gibbs equation, Gibbs free energy equation, that is equal to minus of RT into natural log K. Combining that with equation number 6. For strongly endothermic reactions, the value of delta RH naught may be large and positive. So the value of K will be less than 1 and the reaction is unlikely to form much product. In case of exothermic reactions, delta RH naught is large and negative, and delta Rg naught is likely to be large and negative. That is, the value of equilibrium constant will be greater than 1. We may expect strongly exothermic reactions to have large K and hence can go to near completion. Delta Rg naught also depends upon delta Rs naught. If changes in entropy of a reaction is also taken into account, the value of K or extent of chemical reaction will also be affected depending on whether delta Rs naught is positive or negative. We will quickly write the relation with equilibrium constant. Consider a reaction A plus 2B in both forward and reverse direction, that is reversible reaction 3C plus D. Reaction quotient Q can be written as C to the power of 3 into D to the power of 1 divided by A to the power of 1 and B to the B square. can be defined at any stage of reaction. Reaction quotient Q can be measured at equilibrium. That is, Q is equal to K equivalent. So K equivalent is given as C cube into D square divided by A to the power of 1 B square. I will repeat this because I read it wrongly. K equivalent equals C cube into D to the power of 1 divided by A to the power of 1 divided by B to the power of 2. So standard state can be written as delta R G naught equals delta R H naught minus T into delta R S naught. Or we can also write delta R, the reaction delta GR for a reaction is equal to delta G naught of formation of products minus delta G of formation of the reactants. We can summarize the Gibbs energy change of equilibrium. It is shown in the table below. Delta R G naught value, if it is 0, then log K is equal to 0. That means K value of K will be 1. The equilibrium mixture contains comparable amounts of reactants and products. That means if K is equal to 1, the equilibrium mixture contains comparable amounts of reactants and products. If the value of delta R G naught is less than 0, then the log K will be greater than 0. That means K will be greater than 1. In this case, the equilibrium mixture contains mainly products and exothermic reactions. In the third case, delta R G naught that is greater than 0, then log of K is less than 0 and the value of K is less than 1. The equilibrium mixture contains mainly reactants and endothermic reactions. Please pause this video and note down this table meticulously. Now we'll take up some numerical examples. Question number 3. Calculate delta R G naught for conversion of oxygen to ozone. That is, the reaction is given as 3/2 O2 gaseous forms O3 gas at 298 Kelvin. If Kp for this conversion is the value of equilibrium constant at constant pressure is 2.47 into 10 to the power of minus 29. We know delta R G naught is equal to equation minus 2.303 RT into log of Kp. R is equal to 8.314 joules per Kelvin per mole. It is given. So delta R G naught equals minus 2.303 R, the value of substituting the value of R as 8.314 joules per Kelvin per mole into 298 Kelvin, that is the value of T, into log of Kp. Kp is given as 2.47 into 10 to the power of minus 29 in question itself. Therefore, simplifying, we will get 163,000 joules per Kelvin per mole. That is 163 kilojoules per Kelvin per mole. Next question. Find out the value of equilibrium constant for the following reaction at 298 Kelvin. So the given equation is 2NH3 gaseous plus CO2 gaseous The reversible reaction forms NH2CON NH2 aqueous plus H2O liquid. Standard Gibbs energy change delta RG naught at the given temperature is minus 13.6 kilojoules per Kelvin. Applying log K is equal to minus delta RG naught joules per mole divided by 2.303 RT. That is rearranging the standard formula. Therefore, log K is equal to substituting the value of delta RG naught minus 13.6 into 10 to the power of 3 joules per mole divided by 2.303 8.314 joules per Kelvin per mole into 298. That will simplifying, we get the value as 2.38. Hence, K is equal to anti-log of 2.38. That is equal to 2.4 into 10 to the power of 2. Next question. At 60 degrees centigrade, dinitrogen tetroxide is 50% dissociated. Calculate the standard free energy change at this temperature at 1 atmosphere. So, the given equation is written as N2O4 gaseous forms 2NO2 and the reaction is reversible. This middle symbol shows it is a reversible reaction, 2NO2 gaseous. If N2O4 is 50% dissociated, the mole fraction of both the substances is given by the relation X of N2O4 is equal to 1 minus 0.5 divided by 1 plus 0.5. Therefore, similarly, the X of NO2 is equal to 2 into 0.5 divided by 1 plus 0.5. Therefore, P of N2O4 is equal to 0.5 divided by 1.5 into 1 atm, whereas P of NO2 equals 0.5 divided by 1.5 into 1 atm. The equilibrium constant Kp is given by the relation Kp is equal to P of NO2 whole square divided by P of N2O4, that is equal to 1.5 divided by 1.5 whole square into 0.5, that is 1.33 atm. But delta Rg naught is equal to minus RT into natural log Kp. So, substituting the values, delta Rg naught is equal to minus 8.314 joules per Kelvin per mole into 333 Kelvin into 2.303 into 0.1239. That is equal to minus 763.8 joules per Kelvin per mole. We have come to the end of the chapter, that is unit number 5 on thermodynamics. Let us quickly summarize what we have learned in unit number 5. Thermodynamics deals with energy changes in chemical or physical processes and enables us to study these changes quantitatively and to make useful predictions. We divide the universe into the systems and surroundings. Chemical or physical processes lead to the evolution or absorption of heat Q, part of which may be converted into work W. These quantities are related through first law of thermodynamics, that is delta U is equal to Q plus W, where delta U is the change in internal energy which depends on initial and final states only and is a state function, whereas Q and W depend on the path and are not state functions. We follow sign conventions of Q and W by giving positive sign to these quantities when they are added to the system. We can measure the transfer of heat from one system to another system, which causes the change in temperature. The magnitude of rise in temperature depends on the heat capacity, capital C, of a system. Therefore, heat absorbed or evolved is Q is equal to C, capital C into delta T. Delta T is the change in temperature. Work can be measured by W is equal to minus of P external into delta V in case of expansion of gases. Under reversible process, we can put Px is equal to P for infinitesimal changes in volume, making W reversible is equal to minus P dV. In this condition, we can use the gas equation PV is equal to nRT. At constant volume, W is equal to 0. Then delta U is equal to QV, that is the heat at constant volume, heat transfer at constant volume. But in study of chemical reactions, we usually have constant pressure. Therefore, we defined another state function, enthalpy. Enthalpy change delta H is equal to delta U plus delta Ng into RT can be found directly from heat changes at constant pressure. That is delta H is equal to QP. Here quantity of heat at constant pressure. Here in this equation delta H is equal to delta U plus delta Ng. Delta Ng is the number of moles in gaseous state. There are varieties of enthalpy changes like melting, vaporization and sublimation, which usually occur at constant temperature and can be characterized by enthalpy changes which are always positive. Enthalpy of formation, combustion and other enthalpies changes can be calculated using Hess's law. Enthalpy change for chemical reaction can be determined by delta RH is equal to sigma AI delta FH of products minus sigma I of BI into delta FH reactants. So A and B are coefficient or stoichiometric coefficients. In gaseous states, delta RH is equal to sigma of bond enthalpies of reactants minus sigma of bond enthalpies of products. First law of thermodynamics does not guide us about the direction of chemical reactions. That is, what is the driving force of the chemical reaction? For isolated system, delta U equal to 0. We define another state function, capital S, that is entropy. For this purpose, entropy is a measure of disorder of randomness. For a spontaneous change, total entropy change is positive. Therefore, for an isolated system, delta U is equal to 0 and delta S is greater than 0. So, entropy change distinguishes a spontaneous change while energy change does not. Entropy changes can be measured by the relation delta S is equal to Q reversible divided by T for a reversible process. Q reversible by T is an independent path. is independent of path. Chemical reactions are generally carried out by constant pressure. So we can define another state function Gibbs energy, capital G, which is related to entropy and enthalpy changes in the system by the equation delta Rg is equal to delta Rh minus T into delta R of S. For a spontaneous change, delta G system is less than 0 and at equilibrium, delta G system equals 0. Standard Gibbs energy change is related to the equilibrium constant by the relation delta R G naught is equal to minus RT into natural log of K, where K is the equilibrium constant. The equilibrium constant K can be calculated from this equation, and if we know the value of delta R G naught from the relations delta R G naught is equal to delta R H naught minus T into delta R S naught. Temperature is an important factor in the equation. Many reactions which are non-spontaneous at low temperature are made spontaneous at high temperature. For systems having positive entropy reactions. With this conclusion of summary of chapter on thermodynamics, we will take up MCQs. Question number 1. Which of the following process is non-spontaneous process? 4 options are given. You please go through all the options and mark your answer. So remember that the non-spontaneous process flow of heat from a cold body to a hot body in contact. So here some work is done for transferring heat from cold body to hot body. Next question. At absolute zero, the entropy of a pure crystal is zero. This is, so use 4 options are given. First law of thermodynamics, second law, third law and 0th law of thermodynamics. So the correct answer is third law of thermodynamics, which deals with entropy of pure crystals. Next question. At dynamic equilibrium, the reaction on both sides occur at the same rate and the mass on both sides of the equilibrium does not undergo any change. This condition can be achieved only when the value of delta G is, 4 options are given, -1, +1, +2 and 0. You please go through and mark the correct answer. Recall that at equilibrium delta G equals 0. So option D is the correct answer. Next question. Which of the following is not correct? Please underline not correct. Delta is 0 for reversible process. Delta G is positive for spontaneous process. Delta G is negative for a spontaneous reaction. Delta G is positive for a non-spontaneous reaction. So option B is not correct. Please mark it. Next question. The given enthalpy diagram represents which of the following reactions? So the diagram is shown here. Please note that the total enthalpy of reaction HR is higher than the total enthalpy of product which is given at the lower level. So in this case delta RH, that is net heat evolved in the reaction, is negative. So the 4 options are given. You read all the 4 options. Endothermic reaction, exothermic reaction, reversible reaction, and spontaneous reaction. Pause the video, analyze, and I will give the answer. For exothermic reactions, H reaction is greater than H of products. Therefore, delta H is negative. So the correct answer is exothermic reaction. Please mark it. Next question. Match the column 1 with column 2 and mark the appropriate choice. So column option 1 has four answers, reactions are given. State function option B, that is B is capital B is delta H is equal to Q, and column number column 1 C is delta U, choice is delta U is equal to Q, and intensive property is given in the column number 1. You have to match this with the items given in column number 2. In column number 2, serial 1 is at constant pressure, serial 2 is specific heat, serial 3 is entropy, and serial 4 is at constant volume. You have to match it correctly. Analyze and match it. I will give the explanation. You have to remember the properties. That is, state function is entropy is a state function, and option B is, and that is match item B is capital B is delta H is equal to 2. It is at constant pressure, and delta U equals Q is at constant volume. At constant volume, delta U is equal to Q, and intensive property is the specific heat is the intensive property. So all these options are given as option A. Please remember this. All the properties, that state function is a entropy is a state function. At constant pressure, delta H is Q, and at constant volume, delta U is equal to Q, and specific heat is a intensive property, and you match it. Next question. In isolated system, find the condition for spontaneous reaction. This is a previous year's question of Ameenz. So 4 options are given. You read all the 4 options and pause the video and mark your answer. I will give the solution. For an isolated system, Q equal to 0, W equal to 0. Therefore, delta U is equal to 0. So this can be either option A or option C. For spontaneous reaction, delta G is negative, that is less than 0. This is given in option C. So you please mark option C as the correct answer. Next question. The state of gas can be described by quoting the relationship between. So this is an NCERT exemplar question. So 4 options are given, and option D has given 4 properties, that is pressure, volume, temperature, and amount. So this is the correct answer. So remember and mark option D as the correct answer. Now we'll take up next question. In which case the change in entropy is negative? So 4 cases are given: evaporation of water, expansion of gas at constant temperature, sublimation of solid to gas, and the last option is 2H in gaseous state becomes H2 in gaseous state. Solution is, in the case of 2H in gaseous state reacting to form H2 gas, the number of molecules decrease. That is, initially before reaction it was 2, after reaction it is 1. Hence, entropy is negative. Option D is the correct answer. Next question. The unit of entropy is, this is the question asked in 2020. 4 options are given: joules per Kelvin per mole, joules per mole, per joules, joule per Kelvin per mole, joule Kelvin per mole. The correct answer you have to remember and mark it as A. Next question. An ideal gas undergoes isothermal expansion at constant pressure. During the process, so we have to identify the process. During the process, what happens? 4 options are given. You please pause the video and read all the 4 options, and I will give the correct answer. For an isothermal expansion of an ideal gas at constant pressure, delta H is equal to N into specific heat at constant pressure into delta T, that is equal to 0. Therefore, the value of delta S equals N into R into natural log Vf by Vi, that should be greater than 0. Therefore, the correct answer is enthalpy remains constant but entropy increases. So therefore enthalpy is 0. Please mark this question. This correct option. Next question. For a given reaction, delta H, the value of delta H is equal to 35.5 kilojoules per mole and delta S is equal to 83.6 joules per Kelvin per mole. This reaction is spontaneous at, assume that delta H and delta S do not vary with temperature. This is asked in NEET examination. 4 options are given. Option A, T greater than 425 Kelvin. Option B, all temperatures. Option C, T greater than 298 Kelvin. And option D is T is less than 425 Kelvin. You have to make calculations using the standard formulae and mark your correct answer. So for spontaneous reaction, delta G is less than 0. That is, delta RH minus T into delta RS should be 0. Or T should be greater than delta H by delta S. That is, T should be substituting the given values. Delta H is 35.5 into 1000 joules per mole. That is, 1000 is for converting kilojoules into joules, divided by delta S is 83.6 joules. So simplifying, we get the answer as T should be greater than 425 Kelvin. This is given as option A. Please mark it. With this, we come to the end of our lecture on thermodynamics, comprising of three parts: video 1, lecture 1, lecture 2 and lecture 3. Next lecture, we'll discuss about a new chapter, that is unit number 6 on equilibrium. Till then, goodbye.